Hello everyone, my name is Anna and I will be presenting our poster looking at the false positive potential of tractography connections and how these can be used in network spreading models. This work is motivated by Alzheimer's disease, which is the leading cause of dementia. And a major challenge remains in understanding how the disease pathology propagates through the brain. So there are a range of hypothetical disease propagation models, each based on different theories of how pathology spreads. Ultimately, we want to be able to compare these models quantitatively to test which is most likely. One group of these disease propagation models is network spreading models. These models simulate the spread of Alzheimer's disease pathology through the brain structural connectome. These models work by initially seeding the disease in regions, which we call the epicenter, at time zero, and allowing the disease to spread along structural connections with time. This produces a final estimate of pathology accumulation. There is a major limitation in this work, that the structural connectomes, estimated by tractography, are subject to a high rate of false positive connections. So we hypothesize that false positive connections are a major factor in inaccuracies in network spreading models. And with this in mind, our work has two aims. Firstly, to propose a method to evaluate the potential of each connection produced by tractography to be false positive. And secondly, to incorporate this false positive potential into a network spreading model to moderate the pathology prediction. We calculate a false positive potential for each tractography connection by simulating diffusion images with and without the connection. If a removed connection results in a significant change to the simulated image, we assign a low false positive potential, as the connection is necessary to explain the data. If the removed connection results in a small change, we assign a high false positive potential. We construct a large set of sample connectivity matrices in which we use the false positive potential to provide a probability that each connection appears in each sample. We run these sample connectivity matrices through a network spreading model to produce a false positive informed prediction of pathology accumulation. We compare this to a benchmark prediction calculated by running the network spreading model with the original connectivity matrix from tractography. Here we show the false positive potential of connections in the brain. Yellow corresponds to a high false positive potential, and blue corresponds to a low false positive potential. Here we see regions close to the cortex resulting in a lower false positive potential, whilst a large proportion of connections running through central regions had a higher false positive potential. Many potential pathways run through the central regions, meaning any individual pathway is not essential to explain the data, leading to a high false positive potential. On the other hand, connections in the cortex tend to explain the data more uniquely, resulting in a low false positive potential. Here we see patterns of predicted and observed tau accumulation. The false positive informed model is able to correctly reduce the prediction of tau accumulation in regions overestimated by the benchmark model, such as the orbitofrontal and pars triangularis. In this model, we assume the disease starting point to be in the entorhinal cortex. This explains why both the benchmark and false positive informed models overpredict disease accumulation in the entorhinal and parahippocampal regions. In summary, we proposed a method to calculate false positive potential and incorporated this measure into a network spreading model. A limitation of this work is that we assume the starting point for pathology propagation, or disease epicenter, is the same for all subjects. In future, we will test the idea with more realistic models that identify distinct epicenters and personalize other parameters of the propagation process to individual patients. In addition, we'll also be looking into models to estimate the false negative potential of unconnected regions in the structural connectome, as these are equally important. Finally, thank you to everyone who worked on the project, and thank you for listening.